So hello friends, welcome back to our channel Concept with Clarity 1. In this lecture, we will try to discuss the Boolean algebra, Boolean postulates, postulates related to addition, multiplication, and also we will try to see about the DeMorgan's theorems, and we will try to solve some problems using the Boolean postulates. Okay, so in a simple manner, if I talk about the Boolean algebra, okay, so what are the Boolean laws with respect to addition? Okay, we will see this one. For suppose any variable a, okay, any variable a can have any value 0 or 1. When it is added with a 0, okay, a plus 0 is always equal to a. Okay, anything added with a 0 is a, and a plus 1, any variable added with a 1, okay, is always equal to 1. Okay, whatever you have a here in the left hand side, whatever the variables you have, how many number of variables you have, then also when it is added plus 1, it is always equal to 1. A plus 1 equal to 1. Okay, next one, a plus a, when a variable is added with the same variable, then also the result is a only. Okay, and the last one, a plus a bar is equals to, again equal to 1. Okay, a plus a bar is equals to 1. Okay, so these are the four Boolean laws of addition. Okay, similarly I can have Boolean laws for multiplication. Okay, so what are the multiplication laws? Right, so same thing, if you see any variable multiplied with a 0 is always equal to 0, the result will be always equal to 0, and any variable multiplied with 1 will be equal to the same variable. Okay, a into 1 is equal to a, and a into a is also equal to a only, right? Next, a into a bar is equal to 0. Okay, a into a bar is equals to 0, any variable multiplied with its complement of the variable equal to 0. Okay, so these are the simple simple laws, okay, addition law and multiplication law, which are useful for the by using these Boolean postulates, what we can do, we can reduce the number of variables being used in the design. Okay, so this is one thing, and the second one is DeMorgan's law. Okay, DeMorgan's theorem. Okay, what does a DeMorgan's theorem say? Okay, DeMorgan's theorem say when a plus b whole bar, okay, here we are talking about two variables a and b, so a plus b whole bar is equals to a bar into b bar. Okay, that means indirectly a plus b whole bar is shown as like this, it's a NOR gate. Okay, it's a NOR gate. The equivalent of this is nothing but, you see here complemented input AND gate. My inputs are a and b only. My inputs are a and b only. A plus b whole bar equal to a bar dot b bar. Okay, so you see here for suppose if I take an NOR gate, if a and b are my inputs, okay, then a plus b whole bar is my output. Okay, similarly this is an AND gate with the complemented inputs. You see here actually my inputs are a and b, but the actual input going to this AND gate is a bar and b bar, hence the output of the AND gate is nothing but a bar dot b bar. Okay, so this is the first theorem, a plus b whole bar equal to a bar dot b bar. Okay, this theorem can also be proved by using the truth table. So what does the truth table say? This is a, b, okay, so 0 0 0 1 1 0 1 1, right, and I can have a bar, this is 1 1 0 0 complement of a, and I can have b bar complement of b, that is 1 0 1 0. Okay, and I can have a plus b, one case. Okay, what is a plus b? It is nothing but OR gate 0 1 1 1, a plus b whole bar is equals to, you see here this is 1 triple 0, right. Similarly I can have already I have a bar and b bar. If I multiply a bar into b bar, then you see here 1 into 1 is 1, 1 into 0, 0 into 1, and this is nothing but 0 0 0. Okay, therefore if you see if you see both the truth tables a plus b whole bar and a bar dot b bar both are same, hence these are equal. Okay, a plus b whole bar is equals to a bar dot b bar. This is first law. And second one, a into b whole bar, if I take a into b whole bar, that is NAND gate. Okay, this is equals to a bar plus b bar. Okay, that means you see here a into b whole bar is nothing but my NAND gate. Okay, if I give a b here, this will be a into b whole bar. Okay, this gate is equivalent to the complemented inputs of the OR gate. Okay, complemented inputs of the OR gate. That means this is a and b. The actual input going to this is a bar and b bar. This is equal to a bar plus b bar. Okay, therefore two laws for DeMorgan's theorem. Okay, so the proof can be same thing. By using truth table you can prove it. Okay, so you see here, first one was a plus b whole bar is equals to a bar dot b bar, and second one a b whole bar, a into b whole bar equal to a bar plus b bar. Okay, these two are the DeMorgan's theorem, right? DeMorgan's theorem. Okay, these are also useful for the minimization of the Boolean function. Okay, and the third one, the other postulate, another one important one is nothing but a plus a bar b. A plus a bar b is always equal to a plus b. Okay, and the other one, a bar plus ab is equals to a bar plus b. Okay, this is also we can prove. Okay, a plus a bar b equal to, this term will go off and this will be simply a plus b, and a bar plus ab equal to, this term will go off, this will be simply equal to a bar plus b. Okay, so you can see the simple proof here. Okay, what is the proof? You can see here, this is a plus a bar b. Okay, I will take the LHS. How I can write this one? I can write this is a into 1 plus b. Okay, because when I add 1 plus b, it is equal to 1, and a into 1 is equal to a, so I can add this one. This is a bar b. Okay, so now you multiply this. This is a plus ab plus a bar b. Okay, so this is equal to, you take b common here. Okay, this is a plus b into a plus a bar. Okay, a plus a bar equal to 1, b into 1 equal to b, therefore equal to a plus b. Okay, a plus a bar b is equals to a plus b. This is the simple proof, right? Similarly, I can have a bar plus ab equal to a bar plus b, right? So this is nothing but, you see here, same, I will add a bar into 1 plus b plus ab. So this will be a bar plus a bar b plus ab. Okay, that is equals to a bar plus b into a plus a bar, that is equals to a bar plus b into 1, that is equals to a bar plus b. Okay, therefore you can also write this is a bar plus ab equal to a bar plus b. Okay, most of the times this proof might be asked for you in the examination. Okay, might be for 2 marks or 3 marks. Okay, this can be asked. Okay, this proof a plus a bar b is equals to a plus b, and a bar plus ab is equals to a bar plus b. Okay, please remember all those things. Right, now let me take, so by combining all these things. Okay, so by combining all these things, let me work out some example. Okay, you can see here, for suppose just minimize. Okay, minimize, let us take one equation, a bar b plus a bar bc plus a b bar c b plus a b bar c bar. Okay, by using Boolean laws. Okay, wherever applicable. Okay, so kindly remember in digital electronics. Okay, in digital electronics, right? So every answer is a correct answer. There is no wrong answer. Okay, because I can take some common. I can take because I have, let us say I have 4 product terms here. Right, I can take anywhere common. Right, I can take any, any, I will choose any 2 product terms, and I can take any common variable, right? So wherever I find out, okay, so I can find out the common variable in some, some product terms, the other one can find out in other product terms, right? So all the answers are correct answers only until and unless we are, it is minimized to a larger extent, okay, final extent, right? So we will try to solve this one, okay. So f is equals to a bar plus a bar b plus a bar bc plus a b bar c plus a b bar c bar, okay. So first of all, whenever we are dealing with the Boolean functions, you need to know, right, okay, how many inputs in this Boolean function. How many inputs? Inputs are these things, okay, a b. In the whole equation, you see how many inputs are there. I have 3 inputs, okay, 3. What are those? A comma b comma c. So the output equation is a combination of, I can have a bar, b bar, other things, okay, c and all, c or c bar, right? So how many inputs? I have 3 inputs. And how many outputs? How many outputs equal to 1? What is that output? F is my output, right? So let us try to apply the Boolean postulates, whatever we have learned here. Now I will try to see here. For suppose you see here, f is equals to a bar b. I will take the first 2 terms as the a bar b as the common, then this will be 1 plus c, okay. In the next this thing, I will take b bar c. No, only a is common, right? A b bar is common. A b bar is common. So I will take this as c plus c bar, correct? So that is equals to a bar b. 1 plus c is 1 plus a b bar into c plus c bar equal to 1. This is equals to a bar b plus a into b bar, correct? So this is equals to, what is this? A bar b plus a b bar is nothing but a simply exclusive OR gate. F is equals to a XOR b. So if I am asked to realize the circuit, okay, if I am asked to realize the circuit, this is F is equals to, simply I will take one XOR gate, a, b and a XOR b, okay. So if I don't apply the Boolean postulates, okay, if you see here this equation, how many AND gates, okay. So here I have 1 AND gate, 2 AND gates, 3 AND gates, 4 AND gates, okay. This is 2 input AND gate, this will be 3 input AND gate, right? So 1, 2, 3, 4 AND gates, 1 4 input OR gate, and also I need NOT gates 3 for A, B and C, A bar because I have A bar, B bar and C bar, okay. So if I don't apply the Boolean postulates, then 4 AND gates, okay, 1 4 input OR gate and 3 NOT gates, okay. Total gates were 4 plus 1 plus 3, that is 8 gates, okay. Here I am using only 1 gate, okay. So for suppose if the cost of each and every gate is, let us say 1 rupee, 1 gate equal to 1 rupee, okay, then okay, if I don't apply, if Boolean postulates were not applied, Boolean postulates were not applied, then my design, okay, the cost of the design was 8 gates, so 8 rupees. Now after applying Boolean postulates, my cost of the design is equal to 1 rupee. So 1 by 8 you have reduced the design cost, okay. So for suppose if more number of gates, for let us say 1 lakh gates are being used, okay, then your overall cost of the system gets reduced by 8 times, okay. So that is why we go for applying the Boolean postulates and all, right. So I hope you have understood the concept. Simply you can apply all these laws, okay, with respect to addition, multiplication, okay, and the DeMorgan's theorem. You can apply this to the any Boolean function and you can minimize the Boolean function, and you can design it. Okay, just try to remember how to calculate the number of inputs and the number of outputs for that particular design. Okay, I hope you have understood the concept of Boolean functions, Boolean algebra. Okay, and how to minimize the Boolean function. Okay, so if you have understood the concept, then please like the video, share to your friends and subscribe the channel. Thank you for watching.